Today I'm going to talk about Dijkstra's algorithm. Dijkstra's algorithm is an example of a greedy algorithm. In general, the greedy algorithms take the best decision in each step. We use Dijkstra's algorithm to find the shortest path from one node to any other nodes. And the outcome of the Dijkstra's algorithm would be acyclic, which means that you're not going to see any cycle in the outcome of the algorithm. Let's consider an example. To program this algorithm, we need three things. We need adjacency list, we need the visited list, and we need a priority queue. So the adjacency list holds the edges adjacent to any node. So for example, for V1, the node V1, we have V1 V3, the edge V1 V3 with a cost of 2. From V1 to V5 we have cost of 2. From V1 to V6 we have a cost of 8. V1 V7 we have a cost of 4. Now we find the adjacency list for all of the vertices that we have in the graph. Now for V6 we are not gonna have any adjacency list because nothing is going out of V6 to any node. So V1 is going to V6, V7 is going to V6, V3 is going to V6, but from V6 we're not going to go to any node in the graph. So that's why we don't have anything for adjacency list for V6. And for V7 we have V7, V6 with a cost of 1. Now let's start the algorithm. The first thing that you need for Dijkstra's algorithm is a starting node. So let's say that a starting node that we have for our example is V1. So when we visit a node, we're gonna put the adjacency list of that node into our priority queue. So V1 has this adjacency list and we add it to our priority queue. Now the next step in the algorithm is to get the smallest cost and pop it out of this priority queue. So here the smallest is 2, but we have a tie between V1 and V5 and V1 V3. In the case of having a tie, we just say that just randomly take one out. So let's say we take V1 V3 out. Since we're taking V1 V3 out, we say okay, we have already visited V1, but we have not visited V3. So we're going to put V3 in our visited list and then add the adjacency list of V3 here. But remember that we're adding a 2 to all of these weights. The reason for that is because we are effectively saying that we're going from V1 to V3, and we're going from V3 to these nodes. So the cost of getting to V3, first of all, is going to be 2. So it's going to be 2 plus 4 and 2 plus 5. So that's why we have this plus 2 in here. Okay. Now we go to the next step, which is going to be again taking the smallest one out. So V1, V5. V1 is already visited, but V5 has not been visited. So that is a valid option for us. So we take that edge, and we're gonna visit 5. So 5 is going to be in the visited list, and then we're adding the adjacency list. And again, remember that here we're saying that we're going from V5 to V7, but the cost of going to V5 itself is a 2. So it's going to be a cost of 2 plus a 2. So that is the most important part of the Dijkstra's algorithm, that you update the weights of the edges as you move on. Okay. Now the next option is going to be V1, V7, and then with a cost of 4. So if we are adding the adjacency list of V7, we're going to say, so the cost of getting to V7 was a 4. Now if I add the adjacency list with a weight of 1, I have to also add this 4 to it. So it's going to be 1 plus 4, which is going to be a 5. Now the smallest one here is going to be V5, V7, but we're not going to add we're not going to consider this edge because V5 and V7, both of them are already visited. Now The next thing that we look at is going to be V7, V6 with a cost of 5. We add the adjacency list of V6, but the adjacency list of V6 is just practically nothing. So we move on to the next one. We do the same logic, so it's going to be V3, V4, and then we add V4 to our visited list. We add the adjacency list of V4 to our priority queue, and the cost of going to V4 was 6. Now we're adding 6 to all of the weights from the adjacency list pairs, and then we move on to the next thing, the next smallest thing, which is V3, V6, but we're not adding it because V3 and V6 have been already visited. We go to the next one, which is V4, V1, and the same thing, because they were both visited, we're not going to consider it. We go to V4, V2 as the smallest, as the next smallest, and we say, okay, we haven't seen V2, so we're adding V2 to our visited list, and then we are putting the adjacency list of V2 into our priority queue. Then, as you see, V2, V1 is the next smallest, but V2 and V1 both have been visited, so we're not considering it. V2, V5 with the cost of 18 is the smallest one, and we're not adding it because V2 and V5 are already in our visited list. So there, this is the end of the algorithm, and we started with this graph, this big graph, and then we ended up with this guy here. As you see, we have found the smallest cost from going for going from V1 to any other node. So if we're going to V2, the smallest cost in this graph is going to be 2 plus 4 plus 2, which is going to be 8 units of work. Okay, so as you see, we can go from V1 to V6 with a cost of 5 versus going with a cost of 8. So we have found all of the smallest, all of the shortest path from V1 to any other node in the graph.